In molded pulp fiber operations, issues like inconsistent drainage, extended cycle times, and uneven sheet formation often stem from a frequently overlooked detail: screen selection. Many operations rely on mesh count as the primary specification, assuming it dictates performance, which it does, kind of. The assumption often leads to mismatched expectations, where two screens labeled with the same mesh count often perform very differently once installed, creating production inefficiencies that are difficult to diagnose. A more accurate way to evaluate performance is by focusing on percent of open area, which represents the portion of the screen that allows water to pass through. Open area directly influences drainage speed, vacuum efficiency, and fiber distribution, providing a much clearer picture of real-world performance than mesh count alone. To understand why open area influences performance, it is important to break down the three core variables of the woven wire screen: mesh count, wire diameter, and open area. While these terms are used interchangeably in specifications, they interact to determine how a screen behaves. Mesh count refers to the number of openings per linear inch. While it defines the general scale of filtration, it does not describe the size of those openings or the flow capacity. Wire diameter describes the thickness of each individual wire. Thicker wires increase durability but shrink the openings, while thinner wires create larger openings and allow more flow, but possess reduced mechanical strength. When you combine mesh count and wire diameter, you determine the aperture size, or the actual space between the wires. This is really important because two screens with the same mesh count can have completely different opening sizes depending on the wire diameter used. From there, we arrive at the percent of open area, which measures the portion of the screen that is open space versus solid wire. It's calculated based on both aperture size and wire diameter, serving as the most complete representation of fluid capacity. Because changing the wire diameter while keeping the mesh count constant significantly alters the open area, two screens with identical mesh counts can behave very differently. One may promote fast drainage, while the other creates bottlenecks, making it impossible to predict performance without considering all three variables. In molded pulp forming, drainage dictates how quickly a product is formed and its overall consistency. Once the slurry is deposited, a vacuum system pulls water through the screen. Because open area determines the pathways for the water to exit, it acts as a defining factor for efficiency. Higher open area provides a greater portion of surface space, allowing fluid to pass through more freely. This reduces the pressure drop across the screen, meaning the vacuum system does not have to work as hard, which improves energy efficiency and maintains consistent suction across the mold. Conversely, when open area is too low, resistance increases and vacuum distribution becomes more uneven. This leads to slower fiber capture in some areas and over-compaction in others, negatively impacting speed and product consistency. Optimizing open area creates a balanced system characterized by faster drainage rates, improved vacuum response, lower energy demand, and more uniform suction. And these improvements are directly tied to throughput. Faster drainage shortens forming cycles, increasing the number of parts produced per hour, while stable vacuum performance maintains consistent wall thickness and minimizes defects. Open area acts as the vital bridge between screen design and process performance. Screen selection mistakes often stem from relying too heavily on mesh count. Treating it as the primary decision factor creates performance gaps because, as noted, it does not tell the full story of how a screen behaves under process conditions. A common mistake is assuming that identical mesh counts guarantee identical performance. This oversight leads to unforeseen issues with cycle times and throughput. When open area is insufficient, drainage slows, compounding into measurable losses in hourly output. Furthermore, screen selection based solely on mesh count can cause inconsistent sheet formation, resulting in variations in wall thickness, weak spots on edges, or poor surface finish. These issues are frequently misattributed to vacuum settings when they actually stem from flow restrictions caused by imbalanced open area. There's also the tendency to default to heavier wire constructions for durability without evaluating the trade-offs. While thicker wires increase wear resistance, they restrict flow. In many cases, slightly adjusting the wire diameter while maintaining the same mesh count can increase the open area to improve drainage without sacrificing screen life. To avoid these pitfalls, manufacturers should shift their focus. Instead of merely asking for a specific mesh count, they should evaluate the drainage times required for their cycle times, and the efficiency of their vacuum system across the mold, and whether their current screen is maximizing the available open area. By placing mesh count in the proper context along with wire diameter and open area, operators can fine-tune output, improve consistency, and and reduce inefficiencies. Thanks so much for watching. If you have any questions, click on our Talk to Us button to get in contact with our many experts on woven wire mesh. And if you'd like to learn more about woven wire mesh or our many products, we have a learning center filled with written and video content to make you an expert. We also have a YouTube channel. And don't forget to click that subscribe button and ring that bell to keep up with all things Havre and Boker. Once again, my name is Andrew Kotlar, and I'll see you around in the next video. Bye for now.